This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to our discussion on the fascinating world of simple harmonic motion, SHM. Today we'll be exploring two resources that offer interactive simulations of SHM, focusing on how these tools can help us understand this fundamental concept in physics. Our first resource is a vertical spring simulator found on iwant2study.org. What immediately strikes you about this type of simulation?
The immediate appeal is its visual nature. For students aged 17-18, seeing a mass oscillating on a spring, coupled with real-time graph of displacement, velocity, and acceleration, makes the abstract concepts of SHM much more concrete and intuitive. It allows for experimentation, changing parameters like mass, spring constant, and damping to observe their effects on the motion.
Exactly. The simulator lets you input your own model for the motion, y equals effect. Why is this feature particularly useful for learning?
It encourages active learning. Instead of passively observing, students are challenged to create their own mathematical models to describe the observed motion. This process reinforces their understanding of the relationship between the physical system and its mathematical representation. It also allows them to explore non-ideal scenarios, where the simple harmonic model might not perfectly fit the real-world behavior.
Let's move on to the second resource, which appears to be a more comprehensive online learning platform with various interactive physics simulations, including one specifically focusing on forced oscillations. What are the advantages of having a broader platform like this?
A broader platform provides context. SHM isn't an isolated topic. It's connected to other concepts like energy, forces, and waves. Having access to related simulations and learning materials within the same platform helps students build a more holistic understanding of the subject. The inclusion of questions and activities further enhances the learning experience, encouraging critical thinking and problem solving.
The platform includes questions like, under what conditions would this vertical spring mass system's motion be not well modeled as a simple harmonic motion? How would you approach answering this question using the simulation?
I'd use the simulation to explore the limits of the linear model. By increasing the amplitude of oscillation, I'd observe if the restoring force remains proportional to displacement. If it deviates significantly, it indicates that the simple harmonic model is no longer a good approximation. Factors like the spring's physical limitations, hyperextension, would also be considered.
The platform also asks students to propose velocity and acceleration models. How would you guide students in developing these models?
I'd guide them to use calculus. Since velocity is the derivative of displacement with respect to time and acceleration is the derivative of velocity, they can derive the velocity and acceleration equations directly from their displacement model. The simulation can then be used to verify these derived models by comparing the simulated values with the calculated ones.
The resources also mention a YouTube video demonstrating a splay paint oscillator creating a sine wave. How does this real-world example connect to the simulations?
It bridges the gap between theory and practice. The video visually demonstrates the concept of SHM in a tangible way, showing how a seemingly simple system can produce a predictable, periodic motion. This reinforces the mathematical models explored in the simulations, making the connection more meaningful.
Both resources emphasize the importance of mathematical modeling. Why is this so crucial in understanding SHM?
Mathematical models provide a precise and quantitative description of the system's behavior. They allow us to predict the motion under different conditions and to analyze the relationships between various parameters. This is essential for a deeper understanding beyond just qualitative observations.
The second resource includes a section on energy work power, which is closely related to SHM. How would you connect these concepts?
In SHM, energy is constantly exchanged between potential and kinetic energy. The simulation can visually represent this energy transfer, showing how the potential energy stored in the spring is converted into kinetic energy of the mass, and vice versa. This helps students understand the conservation of energy principle in the context of oscillatory motion.
The platform also features a spring pendulum simulation. How does this extend the concept of SHM?
The spring pendulum introduces a coupled system where the motion is a combination of simple harmonic motion, vertical spring, and pendulum motion back and forth. This demonstrates that real-world systems often exhibit more complex behavior than simple idealized models. The simulation allows students to explore the interplay between these two types of motion and observe the resulting patterns.
Both resources utilize interactive simulations. What are the pedagogical advantages of this approach?
Interactive simulations offer a dynamic and engaging learning experience. They allow students to actively participate in the learning process, experimenting with different parameters and observing the consequences. This hands-on approach fosters a deeper understanding and retention of the concepts compared to passive learning methods.
The second resource mentions damping. How does this factor affect the SHM model?
Damping represents energy loss in the system, typically due to friction. In the simulation, damping reduces the amplitude of oscillation over time, eventually leading to a complete stop. This demonstrates that real-world SHM is often not perfectly sustained, and the damping factor needs to be considered for a more accurate model.
Finally, what is the overall value of these interactive resources in teaching SHM to students aged 17-18? These interactive resources provide a powerful combination of visual representation, active learning, and real-world connections, making the often abstract concepts of SHM more accessible and engaging for students. They encourage exploration, experimentation, and critical thinking, leading to a deeper and more lasting understanding of this fundamental physics principle. Thank you for this insightful discussion.